In a quiet corner of an old engineering archive, a wooden box sat wedged behind a stack of mislabeled binders. It had been there for decades, unnoticed and untouched. The box was heavier than it looked, its surface darkened by time, its hinges stiff from age. No catalog number marked it, and no record mentioned its contents. When the archivists opened the box during a routine inventory, they found a tightly rolled sheet of parchment wrapped in brittle linen. The parchment was surprisingly well preserved, the material firm but delicate at the edges. Once unrolled on a large table, the sheet revealed a detailed mechanical blueprint. Across the top, in bold, confident lettering, was a title: Brown Sharpe Universal Milling Machine, 1878. The drawing was remarkable for its complexity. It showed a milling machine with a swiveling head, an adjustable table, precise gear assemblies, and multiple axes of movement, features far ahead of what most workshops used at the time. Every line reflected careful calculation, suggesting a tool designed for precision work rather than simple shaping or cutting. However, the most striking detail wasn't part of the drawing itself. Along the bottom margin, written in fading ink, was an added remark: "Interesting idea, but far too delicate for serious industrial work. Providence Manufacturers Review, 1878. It was a blunt dismissal, especially considering what historians now know. The 1878 Universal Milling Machine would eventually become one of the most influential tools in American manufacturing, shaping the development of interchangeable parts, precision machining, and early mass production. Yet here was evidence that, at its debut, major manufacturers had mocked it. Inside the box lay another item, a small leather-bound notebook. The handwriting inside belonged to someone who had observed the machine's earliest demonstrations. The entries were brief, but revealing, summarizing the reactions of factory owners and machinists. They believe the gears will fail under pressure. Some say the moving table is unnecessary. Several insist hand filing remains faster. Others think the entire concept is an unnecessary complication. These notes painted a clear picture. In 1878, many industry leaders saw the universal milling machine not as a breakthrough, but as an over-engineered curiosity. They doubted its durability, questioned its practicality, and clung to the belief that traditional methods would always outperform complex machinery. Yet the blueprint and the journal, preserved together, hinted at something more. Despite the skepticism surrounding it, this machine had continued to exist, to evolve, and ultimately to reshape the way factories operated. The box held the first chapter of a story that industry giants of the time failed to recognize, a story about innovation dismissed before it could prove its worth. And though the blueprint had been hidden away for years, its legacy was anything but forgotten. In the late thoughts, American factories were loud, crowded, and filled with smoke. Steam engines rattled, belts hummed, and sparks flew as machinists filed hammered and planed pieces of iron and steel. Work was measured in sweat, repetition, and the skill of human hands. Any innovation that seemed to slow the rhythm of the shop or risk a mistake was met with suspicion. It was into this world that the Brown Sharpe Universal Milling Machine arrived. From its earliest demonstrations, it drew attention. Not all of it positive. Industry leaders called it unnecessary, delicate, even a joke. The adjustable table, capable of moving in multiple directions, was dismissed as overcomplicated. Traditionalists argued that a fixed table combined with hand filing and basic cutting tools was faster and more reliable. Complex gearing, another signature feature of the machine, appeared to many as a vulnerability. Ironworks and toolmakers scoffed, claiming that the slightest misalignment would render the machine useless. Reports from trade meetings of the era describe open derision. Observers mocked the idea of a universal machine, one capable of cutting slots, curves, and gears at precise angles. Some went so far as to predict that no factory would ever adopt it, insisting that speed and durability could only come from simpler, heavier equipment. Even among machinists, opinions were divided. Skilled operators recognized the potential for accuracy, but pride and habit often outweighed curiosity. Shops that had invested in traditional lathes, planers, and hand tools hesitated. They worried that introducing a machine that relied on fine adjustments might slow production rather than improve it. Yet, Quietly, some small workshops began experimenting. They found that the machine's versatility allowed a single operator to perform tasks that previously required several workers. Gears, slots, and angled cuts could be completed with consistent precision, a capability no standard hand tool could match. These early adopters were careful, almost secretive, knowing that their peers would mock any enthusiasm for what was still widely considered a fragile novelty. Historians note that this tension between skepticism and experimentation shaped the machine's early years. Factories that embraced the universal mill began to see subtle changes. Parts fit together more consistently, error rates decreased, and production time for complex components dropped. Yet even as its potential became apparent, the broader industry continued to cling to convention, dismissing it as a curiosity rather than a tool capable of transforming manufacturing. By 1880, the divide was clear. Major ironworks continued producing the same heavy single-purpose equipment they had for decades. Small shops and innovative toolmakers quietly incorporated the universal milling machine, discovering efficiencies and accuracies previously unimaginable. What seemed like a joke to the giants of the era was quietly proving its value where practicality mattered most. The machine's early critics failed to recognize a simple truth. It was not meant to replace human skill, but to extend it. Its adjustable components and precise gearing were designed to amplify the abilities of experienced operators. For those willing to look beyond the noise and tradition of the industrial floor, the machine offered a glimpse of what the future of manufacturing could be. Even in its first years, the universal milling machine was quietly laying the foundation for mass production, precision tooling, and the interchangeability of parts. It would take decades before the industry giants who mocked it realized that the machine they dismissed was quietly shaping the very factories they depended upon. The Brown Sharpe universal milling machine of about 1878 was unlike anything machinists had seen before. At first glance, it looked fragile. Smaller than the massive planers and lathes that dominated the shop floor, its frame lighter, its components more intricate. Yet every line of its design revealed careful intention. The machine featured a rotating table capable of precise angular adjustments. Gears and shafts were arranged in layered sequences, allowing the operator to cut slots, curves, and complex shapes without the trial and error required by hand filing. Its head could swivel to multiple angles, opening possibilities for precision work that had been impossible on conventional machines. Most importantly, every moving part was adjustable. Guides, slides, and screws could be fine-tuned for exact alignment. To a casual observer, this seemed unnecessary. To a skilled machinist, it meant unprecedented control. Where traditional machines demanded brute force and repetition, the universal mill offered finesse and repeatable accuracy. Early critics dismissed these features. They argued that fine adjustments would loosen over time, that complex gearing could never withstand heavy use, and that the adjustable table was a gimmick unlikely to survive an entire day of production. Trade publications emphasized simplicity and strength over flexibility. The machine was ridiculed for its complexity, even called a toy by some. But those who actually used it discovered a different reality. The ability to perform multiple types of cuts on a single machine saved time and reduced errors. Gears could be cut precisely, slots aligned exactly, and curves shaped with uniformity. A single operator could achieve what previously required several people using separate tools. The design also encouraged maintenance and repair. Unlike some heavier machines, which required entire workshops to realign or rebuild, the universal milling machine was serviceable with standard tools. Components could be adjusted, replaced, or corrected without sending the entire machine back to the factory. This approach allowed small workshops to maintain high accuracy while avoiding downtime. Technological innovation alone did not explain the machine's long-term success. It was the combination of versatility, precision, and maintainability that allowed it to quietly earn a reputation among those willing to experiment. While the industry at large continued to focus on sheer power and mass, these early adopters discovered that control and repeatability could produce superior results. By examining surviving examples of the 1878 design, historians have identified the features that made it revolutionary. The rotating table set a precedent for future milling machines. The universal head design influenced every mill built in the decades that followed. Fine adjustment screws and carefully engineered gear sequences demonstrated principles of accuracy and reproducibility that were unmatched at the time. Despite early criticism, the machine proved its value in real workshops. Its performance quietly shifted expectations for what a milling machine could do. The skeptics had judged the machine by its appearance and complexity, but those who measured its output soon recognized the extraordinary potential hidden beneath the surface. The Brown Sharpe universal milling machine was no toy. It was a tool designed to extend human capability, a bridge between traditional craft and the industrial efficiency that would define America's factories. Its revolutionary features were not immediately appreciated, but they would quietly lay the groundwork for the rise of precision manufacturing. By the early 1880s, a subtle shift was occurring in American machine shops. While industry giants continued to favor traditional heavy lathes and planers, smaller workshops and forward-thinking toolmakers began incorporating the Brown Sharpe universal milling machine into their operations. Its practical advantages became impossible to ignore. Machinists who had once watched the machine with skepticism discovered that it could perform multiple operations with remarkable precision. Gears cut on the universal mill fit perfectly into assemblies. Slots aligned exactly. Complex curves and angled surfaces, once painstakingly hand-filed, were now reproducible with a single setup. Productivity rose and error rates fell. The adjustable table and multi-angle head, once criticized as unnecessary complexity, became the key to its utility. Operators could set the machine for one type of cut, make several components, and adjust quickly for the next task. The time saved was significant, particularly in smaller shops where every minute counted. What the skeptics dismissed as fragility proved to be controlled flexibility. Word spread quietly. Small manufacturers who embraced the mill began sharing results with their peers. Blueprints were studied, machining techniques refined, and workshops developed routines that leveraged the machine's versatility. Over time, what had been considered a novelty evolved into a practical necessity. Factory owners began noticing the difference. Machines capable of producing repeatable, accurate parts allowed for interchangeable components, something almost impossible with traditional hand-filing techniques. Engines, locomotives, and industrial equipment could be built with components that fit together without adjustment. Production times shortened, and the efficiency of these workshops became a model for others to follow. The shift was gradual but decisive. Industry skeptics, initially dismissive, were forced to acknowledge the machine's capabilities. Demonstrations of precision cuts, consistent results, and reduced labor requirements highlighted advantages that no heavy lathe or simple planer could match. Some manufacturers began purchasing the universal mills to remain competitive, even if reluctance lingered. Historians note that this acceptance marked a turning point in American manufacturing. The universal mill was no longer an experiment. It had become a tool that redefined expectations for machine precision. Its design principles, adjustable table, multi-angle head, and precise gearing, were incorporated into subsequent generations of machines, influencing standards across the industry. By the end of the decade, the machine's influence was evident. Shops that had adopted it saw clear productivity gains. Its ability to perform diverse operations with high accuracy reduced the reliance on multiple specialized machines. The universal mill demonstrated that innovation, even when initially ridiculed, could reshape practical workflows and efficiency standards in real factories. The Brown Sharpe universal milling machine had survived skepticism, criticism, and doubt. It had proven that versatility and precision were not weaknesses but strengths. Its quiet acceptance in the small workshops of the 1880s laid the foundation for the rise of American factories capable of mass production, interchangeable parts, and the precision machining that would dominate the industrial era. By this point, the machine that industry giants had once called a joke was no longer merely tolerated, it was essential. Its adoption was a turning point, the moment when a tool dismissed as fragile quietly became the backbone of the factories that would define America's industrial future. With growing acceptance, the Brown Sharpe universal milling machine began to change the way American workshops operated. Its adjustable table and universal head allowed machinists to perform tasks that previously required multiple specialized machines. Gears, slots, angled cuts, and curves could all be completed with a single setup, reducing the need to move workpieces between machines or rely on hand filing. The impact on productivity was immediate. One operator could now complete a sequence of complex operations in the time it previously took 2 or 3 workers. Precision became predictable. Parts produced in one shop would fit perfectly in assemblies built in another, creating the foundation for interchangeable parts, a concept that had been theoretical but was now achievable in practice. Factories that embraced the universal mill began to notice the financial benefits as well. Less labor was required for finishing components, mistakes decreased, and workflow became more efficient. Shops that had once relied heavily on hand tools could now scale production without sacrificing accuracy. Machines that combined versatility with repeatable precision were no longer an experimental curiosity. They were essential tools for economic success. The machine's influence extended beyond individual shops. Toolmakers and engineers started designing jigs, fixtures, and accessories specifically to complement the universal mill. Standardized procedures emerged for cutting gears, milling slots, and shaping curves. Workshops developed a systematic approach to machining that balanced speed and precision, allowing even less experienced operators to produce high-quality parts. The universal mill also encouraged innovation in machine design itself. Competitors began studying Brown Sharpe's approach, recognizing the advantage of adjustable tables, multi-angle heads, and precise gearing. Future generations of milling machines incorporated these features, creating a lineage of tools that carried the original design principles into the 20th century. By the mid-1880s, the universal mill had quietly become the backbone of American factories producing locomotives, engines, and industrial equipment. Its versatility allowed for more complex assemblies and standardized components. Work that once required careful hand filing by skilled artisans could now be completed with repeatable accuracy, freeing operators to focus on efficiency and productivity rather than improvisation. Historians note that the machine's role in promoting precision and repeatability cannot be overstated. It enabled the first generation of mass-produced industrial components, creating a practical system for building machines that could be disassembled, repaired, and reassembled with consistent results. The skills of the operator remained important, but the machine amplified those skills and reduced the risk of human error. The universal milling machine also fostered a culture of measurement and quality control. Shops began to track tolerances, inspect parts systematically, and record results in ways that would eventually evolve into modern quality assurance processes. The machine's design encouraged careful attention to geometry, alignment, and repeatability, principles that would define American manufacturing for decades. By the end of the 1880s, the joke machine had transformed production practices across the country. It had proven that innovation, even when initially ridiculed, could redefine industrial work. The universal mill demonstrated that versatility, precision, and repeatability were not just technical advantages. They were the keys to building factories capable of producing America's industrial backbone. The influence of the 1878 Brown Sharpe universal milling machine extended far beyond its immediate adoption in workshops. Its design principles, versatility, adjustable components, and precise gearing, became a blueprint for the future of machine tools. Engineers and machinists recognized that precision could be standardized and maintained, not just achieved occasionally by expert hands. By the 1890s, milling machines inspired by the universal design were appearing in factories across the country. Every new iteration preserved the core ideas of adjustable tables and multi-angle heads. These features allowed operators to produce complex parts with repeatable accuracy, laying the foundation for assembly lines and mass production. What had begun as a small workshop experiment evolved into a guiding philosophy for machine design. The universal mill also shaped the approach to manufacturing documentation. Detailed manuals, diagrams, and specifications became standard practice. Each component, every adjustment, and all maintenance procedures were carefully recorded. Operators no longer relied solely on experience. They could follow instructions to reproduce results consistently. This shift toward documentation reinforced the machine's role as a tool for scalable industrial production. Historians argue that the machine's influence extended even further, beyond individual workshops. Its principles enabled the development of interchangeable parts, a cornerstone of modern manufacturing. Engines, locomotives, and machinery could now be built with standardized components that fit together precisely. The universal mill made these achievements possible, combining accuracy with versatility in ways that earlier tools never could. The design philosophy of the universal milling machine also affected the training of machinists. Apprentices learned to value precision, alignment, and careful setup. They were encouraged to understand the machine's geometry and the effects of each adjustment, creating a generation of operators skilled in both craftsmanship and repeatable processes. These lessons carried forward into every subsequent generation of machine tool operators. Perhaps most importantly, the universal mill demonstrated the value of innovation in the face of skepticism. Industry leaders, who had initially dismissed it as a fragile curiosity, were forced to acknowledge its capabilities. The machine's practical benefits, faster production, repeatable accuracy, and adaptability could not be ignored. Its quiet success proved that even ideas ridiculed at first could become central to industrial progress. By the turn of the century, the Brown Sharpe universal milling machine had firmly established itself as more than a tool. It had become a symbol of American ingenuity. It had quietly transformed the workflow of factories, improved the efficiency of production, and influenced generations of machine tool design. Every major industrial workshop owed part of its success to the principles first embodied in that 1878 machine. Even as new technologies emerged, the legacy of the universal mill persisted. Modern milling machines, lathes, and machine centers trace their lineage back to its design. Its influence can be seen in adjustable tables, multi-angle heads, and precision gears that remain standard in contemporary equipment. The machine that industry giants once mocked had left an enduring mark on American manufacturing, shaping both its techniques and its philosophy. By the early 1900s, the Brown Sharpe universal milling machine had transformed from a dismissed experiment into a critical component of American industry. What had once been called a joke was now quietly proving its worth on factory floors, shaping the nation's manufacturing capacity. Initially, skepticism remained among the largest ironworks and toolmakers. Executives and engineers accustomed to heavy, single-purpose machines were slow to adopt a tool that relied on fine adjustments and multi-angle precision. They questioned whether a delicate machine could survive the rigors of full-scale production. Yet evidence from smaller workshops told a different story. Production times dropped, accuracy improved, and complex components could be reproduced consistently. Workshops that had embraced the universal mill began producing parts that fit together perfectly, reducing the time spent correcting errors. Engines, locomotives, and industrial machinery became easier to assemble, maintain, and repair. The machine's ability to handle multiple operations within a single setup made it indispensable. Its design encouraged efficiency without sacrificing precision, a combination that slowly won over even the most conservative skeptics. By 1910, factories nationwide were rethinking their equipment strategies. Machines that could combine versatility with precision became more desirable than raw size and brute force. The universal milling machine's influence spread not only through adoption, but also through imitation. Competitors began designing machines inspired by its adjustable table, universal head, and precise gearing, ensuring that its principles would endure. Its reputation continued to grow as operators and engineers recognized the economic benefits. Reduced labor, improved quality, and predictable output meant that the machine paid for itself over time. Shops that once relied on hand filing and simple tools now had a system that allowed for standardization and repeatability, critical for the emerging era of mass production. The transformation from mockery to mastery was not sudden. It was gradual, a result of consistent performance and undeniable advantages. Machine after machine demonstrated that versatility and precision could coexist, and that a tool initially dismissed as fragile could outlast heavier, simpler equipment. The universal milling machine quietly became a symbol of practical ingenuity, a bridge between traditional craftsmanship and modern industrial efficiency. Historians note that the machine's journey mirrors the broader evolution of American manufacturing. Innovation is rarely appreciated immediately. New ideas often meet resistance, especially when they challenge established methods. Yet the Brown and Sharpe universal milling machine proved that perseverance, careful design, and real-world utility could overcome doubt, transforming industry standards in the process. By the second decade of the 20th century, the universal mill was no longer an optional experiment, it was essential. Factories producing precision components relied on its versatility. Workshops competing for contracts in engines, locomotives, and industrial machinery depended on the machine's accuracy and reproducibility. What had begun as an ambitious experiment had quietly become the backbone of American industry. The machine's story became a lesson for future generations. Innovation, even when ridiculed, could create transformative results. The universal mill demonstrated that careful engineering, attention to detail, and adaptability were far more valuable than appearances or conventional wisdom. By overcoming mockery, it had secured its place as a masterpiece of industrial design, laying the foundation for the factories that would define America's industrial rise.